I'm going to start where we left off in the last video. In the last video, we were on page 332 in our books. We were on number 3, letter H, the last problem. We had just found that x minus x was equal to 0, and that anything to the 0th power was equal to 1. The reason this example is shared is because it shows you that no matter what we have here, whether it's a number and a power or a variable with a power, either way, if you have the same thing over itself, the result is going to be equivalent to 1, as long as these two exponents are the same. So it doesn't matter if you have 2 minus 2, you'll get 0, or if you have x minus x, you'll get 0, or if you have, let's say, negative 5 minus negative 5, you will also get 0. So it doesn't matter if it's a variable or a number, you're going to get 0, and the final result will be 1. So that means that 0 is equal to z, or z is equal to 0 in number 3. Now we're going to look in our books at page 333, and I'm going to pull this up on the screen. We're going to read it together, and we're going to discuss it. Negative exponents. Suppose that you were hired as a science lab assistant to monitor an ongoing experiment studying the growth of an insect population. If the population when you took over was 48, and it was expected to double every day, you could estimate the population for any time in the future or the past with the function p equals 48 multiplied by the quantity 2 to the power of x. So I want you to picture yourself. You have your lab coat on, you're going into work, and when you took over, the insect population was 48. What's going to happen is that every day you're supposed to have double of what you had the day before. Let's keep reading. Future estimates are easy. One day from now, the population should be about 48 times 2 to the power of 2 to the power of 1, which is equal to 96. 2 days from now, it should be about 48 times 2 to the power of 2, or 48 times 2 times 2, and that equals 192. So on. Estimates of the insect numbers in the population before you took over required division. So when you're moving forwards, you're multiplying by 2. When you're moving backwards, you're dividing by 2. Let's continue reading. One day earlier, the population should have been about 48 times 2 to the power of negative 1, which equals 48 divided by 2. So 48 divided by 2. Then we keep, we change, we flip. So that's where they get this from. And then when you multiply that, you get 48 divided by 2. When you multiply the numerators and the denominators, and that is equal to 24. 2 days ago, it should have been about 48 times 2 to the negative second, which is equal to 48 divided by 2, which is equivalent to this, which is equal to 48 times 1 over 2 to the second power, because we changed the sign to multiplication, and then we flipped 2 squared, so it became 1 over 2 squared. And then that's equal to 12, so it would be 48 times 1 over 2 to the second. We know that 2 to the second is 4. So 48 divided by 4, we get that value of 12. So that's 2 days previous. I think if you think about it, it's pretty easy for you to double or divide by 2. So let's create our table. And let's look at 0, day 0. When you show up in your lab coat, you're looking at the number of insects, it's 48. And you're expecting that the next day you should be at 96. And the day after that you should be at 192. You also know that previous to you coming in the day before, the insect count was at 24. The day before that, it was at 12. And the idea here is that when you're moving forwards, you're multiplying by 2. And when you're going backwards, so you're thinking about the days previous, you're dividing by 2. You're dividing by 2. And when you divide by 2, so you take any number and you divide it by 2, that's the same as keep, change, flip, multiplying by 1/2. So you could also say that when you're going backwards, instead of dividing by 2, you could say, well, really, I'm multiplying by 1/2. They're trying to get you to see that we can change negative exponents into this fractional form and use it in problem situations. So let's look at some examples and think about what this rule looks like. To do that, we're going to justify why 1 over b to the power of n is equal to b to the negative power of n. We're going to use the variables that they have in the book first, or variable, not variables. We're going to use b. And then what I'm going to do is I'm going to show you the same example, but I'm going to use number values instead. So 1 over b to the power of n, this is our starting piece. And we're showing how we can transform that into b to the power of -1 with equivalent steps. So from one step to the next, we always have 2 equivalent values. To get from this beginning to step 1, all you do is you change 1 to b to the 0th. Remember, anything to the 0th power is equal to 1, so b to the 0th is equal to 1. If they are equivalent, you can substitute one for the other. They are the same thing. So b to the 0th over b to the n is what we have in step 1. In step 2, we follow the rule that we just learned. We take the numerator's exponent and we subtract the denominator's exponent. So we take 0 minus n. The difference between 0 and n is -n. So the final result is b to the power of -n. Let's complete another example, and this time, instead of writing 1 over b to the nth power, we're going to do 1 over 7 to the, let's choose 5. Doesn't really matter what we use. So step 1, what we were supposed to do is replace 1 with 7 to the 0th power. It's important that this base is the same as the base in the denominator. So that's step 1. Step 2, we follow our rule and we take the base of 7 and then we take the numerator's exponent and we subtract the denominator's exponent and we get 7 to the -5th power, which is step 3. So we showed a series of equivalent forms to show that 1 over 7/5 is equal to 7 to the -5th. Now normally you're going to start with this piece, 7 to the -5th, and work backwards to 1 over 7 to the power of 5, because in math we don't use negative exponents. We just get rid of that negative exponent. This is the accepted way to have it written. So most math classes are going to ask you to get rid of that negative exponent and write your final answer in this form. Let's do one other example. Let's use 1 over, let's try 15 to the power of 2. So step 1, we replace 1 with 15 to the 0th power. So here is step 1. And then step 2, we use our rule. We write our base, and then we take the numerator's exponent and we subtract the denominator's exponent from it. The difference between 0 and 2 is -2. So we just made it to step 3, and we see that 15 to the -2nd we proved is equivalent to 1 over 15 to the 2nd power. So that brings us to our new rule. We're going to do examples with our negative exponent rule. So this is number 7 in your book. So we're still on page 333. 5 to the -3rd. All right, 5 to the -3rd, I'm going to write over 1. any number that you have, for example, if you had 2 or you had 3, you can write this over 1. So any integer you can write over 1, or any really value you can put over 1 without changing it. So I'm going to represent this as 5 to the negative third over 1. The reason is so that I show the fraction bar. Because what's going to happen is that we're going to flip this over the fraction bar to change this negative exponent to a positive exponent. So I'm going to go ahead and flip this over the fraction bar. And in the denominator now I have 1 times 5 to the negative third, which just equals 5 to the third. Oh, sorry about that. I didn't mean to write 5 to the negative third. When you flip it over the fraction bar, the sign of the exponent changes. So it becomes a positive in this case because it was originally a negative. Now what you need to remember is that any number is technically being multiplied by a factor of 1. So what we have left over up here, I like to call the hidden 1. So we have left over the hidden 1. So the final answer is going to be 1 over 5 to the third. If you try to do this faster, you might want to just put the fraction bar in, circle 5 to the negative third, move it to the denominator, and change the sign of the exponent. That's the key part of this problem. And then you leave your hidden 1 in the numerator. So it's 1 over 5 to the third. And this is the kind of steps that you're going to follow. We already proved that these two are equivalent. So I want you to, now that we've looked at the justification, accept that rule and use that rule. If we started with this and I asked you to go back to 5 to the negative third, all you would do is, again, you would flip this over the fraction bar, and when you flip it over the fraction bar, the sign of the exponent changes. Now we had a 1 in the numerator. We had a 1 in the numerator, but it's not really necessary because 1 times anything is anything, or whatever you multiplied it by is what I mean. And what's left in the denominator? Well, a hidden 1. Anything divided by 1 is whatever was in the numerator, so you just leave it as 5 to the negative third. So we can go from a positive exponent to a negative exponent. We can go from a negative exponent to a positive exponent by flipping over the fraction bar. Let's look at example B. In example B, we have 6 to the negative first, so I'm going to put that over 1. Then I'm going to flip this over the fraction bar. What is left in the numerator is the hidden 1. And then in the denominator, you have 1 times 6 to the power of 1, because the exponent changes from a negative exponent to a positive exponent when it flips over the fraction bar. And then I simplify. So 1 times 6 to the first is 6 to the first. So we really get 1 over 6. All right, let's look at example C. And example C is 2 to the negative fourth. So what I'm going to do is I'm going to write the fraction bar in, and I have the 1 in the denominator. I flip this over the fraction bar, and it becomes 2 to the power of 4. In the numerator, we're left with the hidden 1. 1 times 2 to the fourth is just 2 to the fourth. So we get 1 over 2 times 2 times 2 times 2. 2 times 2 is 4. 2 times 2 is 4. 4 times 4 is 16. And we get 1 over 16. Sometimes you'll be asked to leave it in exponential form, and that means that you leave it as 1 over 2 to the fourth. If you're asked to put it in standard form, it should look like this, 1 over 16. And we're not going to have enough time for another example, so I'm going to stop the video now, and we'll continue in the next video.